Welcome to this next video in the playlist on field theory. In this video what we're going to introduce is a really important concept, the concept of a field extension. Now field extensions are the centerpiece for field theory. They are at the center of everything we will study from now on. Okay, so a really important video. Right, so what are we going to actually talk about then? We're going to firstly look at the definition of a field extension, what even is a field extension. Then what we're going to talk about is a really important but simple observation about field extensions, linking them to the theory of vector spaces, and we're going to see that we can actually use all of the theories that we have in vector spaces and we can apply them to understanding field extensions. So that's an incredibly powerful but, as I say, incredibly simple observation. Okay, and then what we'll talk about is generating a field extension by trying to join on a root to a polynomial that is irreducible currently in the ring of polynomials over your initial field. Okay, so let's begin then with the definition of a field extension. Okay, so this is a really simple concept. It's exactly analogous to subgroups, subrings, subspaces in group theory, ring theory, vector spaces respectively, okay, except that it's told from the opposite point of view, and let me explain what I mean by that. Okay, so normally in other parts of abstract algebra, so groups, rings and vector spaces, when we have one algebraic structure with a smaller algebraic structure inside of it, so this sub-box here represents the smaller algebraic structure and this one represents the larger algebraic structure, normally we always talk about things from the perspective of the larger algebraic structure. Okay, and then we look down at the smaller algebraic structure as a inferior being, as an inferior structure, and we call it a subgroup or a subring or a subspace in group theory, ring theory and vector spaces respectively. Okay? In field theory we do it the opposite way round. Instead of talking about subfields, instead we do it from the perspective of the smaller algebraic structure. So we look from the perspective of the smaller algebraic structure and then look at the larger algebraic structure as a superior being, and we call that a field extension. Okay, so we'll start off with our small field here, so this will be our field, capital F, and I'll just highlight it here in orange. Okay, so here's our starting initial field, capital F, and then we view the larger field that it's contained within as a field extension of F. And a common name for a field extension will be K. So K is just a field that is containing the smaller field capital F, and it's going to be therefore a field extension of the field capital F. So it's exactly the same sort of concept as subgroups, subrings, subspaces, except we tell the story from the opposite algebraic structure's point of view. We always tell it from the inferior algebraic structure's point of view, the smaller one, whereas of course in groups, rings and vector spaces we do it from the perspective of the larger algebraic structure. Okay, so quite simply then, a field extension is just a larger field that contains this smaller field as a subfield. Okay, so just a smaller subset which, with the restricted addition and multiplication laws on it, obeys the axioms of field theory in its own right. Okay, so now the basic notation then. How do we write K is a field extension of F? Well, we write it like so, K / F. Okay, and you should read this as K is a field extension of F. Okay, and this just means exactly what this picture shows. K is a larger field which completely contains the field capital F as a subfield. Okay, so it's just analogous to writing something like this, where you'd read this as F is a subset of K. Okay, you should read this as K is a field extension of F. So do not confuse this notation with quotient ring. Okay, this does not mean perform the quotient of K by F. Okay, if I wanted to write quotient ring, I'd do it more like this. Okay, more on an angle like that, whereas this is all horizontal in this way. Okay, so do not confuse this notation with meaning quotient ring. It means K is a field extension of F. Okay, right, so that's the notation that we'll use to denote that one field is a field extension of another field. Okay, so there's the introductory notation then, and the basic concept of a field extension. It's a really simple concept. Now let's actually look at this simple observation that is going to be absolutely crucial. Okay, so a really important observation about field extensions, which is actually really simple. Okay, so this is this observation. The observation is that if you've got K, which is a field extension of a smaller field F, then you can view this larger field as being a vector space over F. Okay, so you can view this as being a vector space over F, and this is an opportunity to revise our linear algebra. Okay, so how then can we view it as a vector space over F? Well, what was a vector space over a field F? Okay, well, a vector space was first and foremost a set of symbols, so K is certainly a set of symbols, and on it you need to define an addition law and a scalar multiplication law. Okay, now the addition law needs to be all the elements of the vector space adding to other elements of the vector space, and it needs to obey the axioms of an abelian group. Well, that's absolutely excellent, because K is a field, so of course it has an addition law defined on it, and that addition law will obey the axioms of an abelian group. So if I just draw this out here, okay, our larger field K will have this addition law here. Okay, so here is the great big addition composition table, and we're just going to now use this addition table as the addition table for K viewed as a vector space now. Okay, so this obeys the axioms then of an abelian group. Okay. Right, so addition's absolutely fine. Now what we need to check is that we can define a scalar multiplication which will obey the axioms that it needs to obey in order to be a vector space. Okay, so what do we have currently defined on the field capital K? We have a multiplication. Now, the multiplication involves any element of K being multiplied by any element of K. Okay, so I actually write out the multiplication table here. So here's our multiplication table at the moment. Okay, and it obeys all of the axioms of a field. So it obeys the axioms of a commutative ring, along with the fact that all of the non-zero elements have a multiplicative inverse. That's the criterion for being a field. Okay, now, we just want a scalar multiplication. If we're going to view K as a vector space over F, we don't want a multiplication of every single vector with every single vector, no. We want a scalar multiplication where we can multiply elements of the field here with any vector in K. Okay, but of course all the elements of the field are in K. So what in fact we can do is just restrict this table down a bit. Okay, so let's say these rows here, okay, and I'll just highlight those in orange here. So these rows here in this orange section, let's say that these correspond to the elements of the field F, and all of the rest down here correspond to the elements of K that are outside of F. What I claim is that we can restrict this multiplication table down now and get rid of all of this bit, okay? And now that will form a scalar multiplication table, because look, I've now got all of the elements of my field, capital F here, being multiplied with all of the elements of K, which I'm now viewing as the vector space. Okay, so this is looking hopeful that we can use this then as a scalar multiplication table, because that's exactly what the scalar multiplication table should look like. It should be all of the elements of the field being multiplied with all of the vectors in the vector space. Okay? Now what we need to make sure of is that it obeys the 4 axioms that scalar multiplication must obey in order for this to be a vector space. Okay, so this is where we can revise our vector spaces. What are the 4 axioms that a scalar multiplication table must obey in order for this to successfully be a vector space over F? Okay, so axiom number 1 is closure, and this says that if you pick an arbitrary element from the scalar field, so we usually use C to denote an element of the scalar field, and an arbitrary vector from the vector space, so pick, oh, and I've put capital V here, cross that out and put K, because K is our vector space in this case. Okay, so an arbitrary vector, little v, from our vector space, capital K here. It must be the case that when you scalar multiply C with V, and I will omit the multiplication symbol, I'll just write them next to each other as is conventional. This must be an element of the vector space, so it must be back in K. Now, of course, that's going to be true because the entire multiplication table was closed. Whenever you multiplied an element of K with K, you got another element of K. So this sub-portion of this multiplication table is certainly going to be closed. Okay, so that's absolutely fine. So axiom number 1 works fine. Axiom number 2, and I know I'm going to zigzag back and forth just so that we don't waste paper. Okay, so axiom number 2 then is that scalar multiplication must associate with field multiplication. Okay, and I'll write this out in vector space notation firstly. So for all two elements of the scalar field you pick, so C1 and C2 that you can pick from the scalar field capital F, and for all vectors that you can pick from the vector space, so for all v is an element of capital K here, it must be the case that if you consider v scalar multiplied by C2 and then take the answer, which is some vector in your vector space by axiom number 1 here, and then scalar multiply that with C1. So if you consider C1 multiplied with the answer to C2 scalar multiplied with v, where this is scalar multiplication, so multiplication in our scalar multiplication table here, and I might just call this, give it its title, so this is now being viewed as our scalar multiplication table, this restricted version of the multiplication table on the initial field, capital K. Okay, right, so if you ask what is this element where you firstly multiply your vector v by C2 with the scalar multiplication table, and then you take the answer, which is some vector again, and then scalar multiply that vector with C1 here, okay, it needs to be the same as if you firstly multiply the two scalars together, C1 and C2, in the field. And I know this is going to look incredibly trivial in this case, but in more general vector spaces it isn't so trivial. Okay, multiply those two together in the actual field, capital F. Okay, so rather than using the scalar multiplication table, you go into your field capital F. It has a multiplication table on. Okay, and you ask what is C1 multiplied with C2 in that multiplication table on the field. You take the answer, which is some element of the field, and then scalar multiply that with V. Okay, and in this case, because F is a subset of our vector space K, okay, yes, this is incredibly trivial, but more generally, the field will have its own separate operations which might have nothing to do with the addition and scalar multiplication that are on the vector space. Okay, of course these axioms will link the two, but it won't generally be as connected as it is in this case. Okay, right, so this is obvious because of course these scalar multiplications are just the multiplications in our multiplication table of the entire field K here. Okay, and of course multiplication of these two elements in the field, well, the field is just a subset of K, so that's multiplication in the field as well. So this is really just saying, this really just relies on multiplication in the field, capital K, being associative, which of course we know it is. That's one of the axioms ring theory insists must be true for the multiplication table of a ring. Okay, so this follows just from the associativity of multiplication in the field. Okay, now let's go on to axiom number 3 here. So axiom number 3 is that if you take the multiplicative identity of your field, okay, so 1 in the field, and you scalar multiply that with any vector in the vector space, it must just give you the vector back again. Okay, and again, this looks incredibly trivial because of how related the field is to the vector space in this case. Okay, so of course, when you take 1 in the field and multiply it with any element of your vector space K, you are just going to get that element of the vector space back again, because 1 is the multiplicative identity in the field K, and it will multiply with anything to give that thing back again. So because the scalar multiplication table is just the restricted multiplication table on the field capital K, this is also trivial. Okay, so we can tick off this identity one. Now, the final axiom, the fourth axiom, is the two distributive laws that we insist scalar multiplication must obey. Okay, so part 1 is that scalar multiplication must distribute over addition in the vector space. So, for all c that you can pick from the field, and for all two vectors v1 and v2 that you can pick from the vector space, which in this case is k, if you consider what c scalar multiplied with v1 plus v2 is equal to, where this is addition in the vector space, this must equal c scalar multiplied with v1 plus c scalar multiplied with v2 here. Okay, so it must give you the same answer whether you firstly add the two vectors together and then scalar multiply, or firstly scalar multiply and then add. Okay, so this is distributivity of scalar multiplication over addition in the vector space. Now again, because scalar multiplication and addition are just as they are in the field capital K, this just becomes left distributivity, which we know is true for the addition and multiplication operations of the field capital K. So again, this is all very, very trivial because of the incredible axioms that the addition and multiplication table obey in the field capital K. Okay, so again, I'll stress that the way we are defining addition and scalar multiplication is just use the addition and multiplication on the field capital K. All you have to do is restrict your multiplication table down, because we're not interested in this portion down here. We're only interested in an element of the subfield capital F multiplying the larger field extension capital K. Okay, and then the second distributivity that we insist a vector space must obey is distributivity of scalar multiplication over addition in the field. So this involves taking two elements of the field, C1 and C2, which are elements of the field, and taking one vector this time, so 1v, which is an element of the vector space, and considering what is C1 plus C2, where you're adding them together in the field, capital F this time, okay, and then you scalar multiply it with v. Well, the thing that we insist is true in a vector space is that this is C1 scalar multiplied with v plus in the vector space now, so we've gone from having an addition in the field to having an addition in the vector space, C2 times v here. Okay, and again, because addition in the field is just addition in K effectively, because the field F is just a subfield of the field extension K, okay, then this just becomes right distributivity, because scalar multiplication is also just multiplication in K. So this just becomes right distributivity, which we know, of course, is going to be true in our field capital K, because we insist on it being so, since this is a ring. Okay, so there, it does obey the axioms of a vector space. So whenever you have a field extension K, which is a field extension of your smaller field, capital F, you can always view that larger field as being a vector space over the smaller field, capital F. And how can you do that? Well, you just take the normal addition law that you've already got on that field, capital K, you take the multiplication table, okay, you want to turn it into a scalar multiplication table, so you have to get rid of this bottom portion here, because you only now want to be talking about an element of the smaller field, capital F, multiplying an element of the field extension. You don't want to talk about elements that are outside of the smaller field multiplying elements of the field extension. So you're just restricting down the composition laws here, and then you're arriving at vector space operations. So it's all rather nice. Now, why is this such a powerful observation? It's a very simple observation. Why is it such a powerful observation? Because linear algebra, we have explored linear algebra. We know a lot about vector spaces. It now means that we can use the knowledge about vector spaces and apply it to understand field extensions, which is very nice. Okay, and to give you my first example of using concepts from linear algebra and applying it to field extensions, let's talk about the degree of a field extension. Okay, so this field extension K, because we can now view it as a vector space over F, a natural question to ask is, what is the dimension of this field extension? Okay, now it might turn out that the field extension viewed as a vector space over F has infinite dimension. Okay, so there are two possibilities. Either the dimension could be infinite, so the dimension of this vector space could be infinite, or it could be finite, i.e. a finite set of vectors in the field extension K will span the entire vector space when you take a linear combination where the coefficients are from the field capital F. Okay, so there are two possibilities. The vector space could be infinite dimensional, or it could be finite dimensional. Now, infinite dimensional vector spaces, we're not really going to see many of those. Throughout this playlist on field theory, our main focus will be on finite dimensional vector spaces. Okay, and in this case, of course, the field extension will have a constant, a lovely constant associated with it, which will be the dimension of that field extension viewed as a vector space over F. Okay, so we can now ask what is the dimension of this vector space K over F. And we call that constant the degree of the field extension, and we notate it like so. Okay, square brackets, and then you put K colon F here. Okay, and this just means the dimension of the field extension viewed as a vector space over F. Okay, and you call it the degree of the field extension K over F, or the index of the field extension K over F. So you can either call this the degree or the index. Okay, either notation is used. You could refer to it as the dimension. That's not particularly common. People would know what you meant, but degree is what we will generally use to describe this. Okay, so this is a parameter that you can associate with any field extension, provided of course that it is a finite dimensional vector space over the field F. Okay, there are examples of field extensions that are infinite dimensional vector spaces over the smaller field F. Okay, but we're mainly going to focus on those that are finite because they're the really interesting ones. Okay, right, so there is a concept from linear algebra that we have now just applied to field extensions. We now have this concept of the degree or index of a field extension, and it's not going to stop there. We are going to see loads of instances where we use concepts from linear algebra to understand field extensions. Okay, right, so we'll have a break here, and in the next video what we'll turn our attention onto is the huge topic, okay? The topic of taking a field and trying to construct a larger field so that it contains a root to a polynomial that previously was irreducible and had no roots in the field. Okay, so we'll do that in the next video.